All right, so for day 3 of this calculus workshop series that we're doing, we're gonna finally get into some calculus. And the first thing that I wanted to do is just try to give a quick overview of what calculus is all about. Okay. All right, so give me a second. I'm gonna share another application. All right, I think all of you can see me sharing a slide now. All right. So this is a set of slides that I created, as you can see, in 2022, but I'm gonna just go ahead and reuse it for this workshop. Am I on campus? Yes, I am on campus. I am in the library right now because we have some equipment that makes it easier to do recordings and live presentations like this. Okay. I will probably be here tomorrow, yes, because I have a lot of work to do. And yeah, okay, so let me just answer some of these questions real quick. So is there a way you can access the previous workshop notes? Yes, if you go to our YouTube channel, we've been uploading the recordings of our workshops to it, and in the video descriptions, we've been including links to all the notes and other stuff. So I'm going to post a link to our YouTube channel. You can just give me a few seconds. Okay, someone already did it. All right, thanks. And all right, I guess I will now go ahead and get started, okay? So what is calculus? Let's see here. Okay, so in calculus, there are primarily these 3 objects that you're going to be studying. So the first object that you're going to encounter is something called a limit. And we're going to be talking about limits today and tomorrow. And then after limits, you're going to learn about derivatives next in your calculus course. And then finally, you're going to learn about integrals. And so I want to try to introduce what these 3 objects are. And so to do that, I'm going to take a look at this problem here. So I have this kind of weird looking shape, and let's suppose that we want to calculate the area of this figure. So because this is not like a simple shape, you can't simply do like baseline height or something like that. There's no formula for it. So if we wanted to calculate the area, one strategy is the following. So we can divide this area into, here I'm using 4 pieces, but the number 4 is not special. And what we're going to do is we're going to approximate the area of each of these pieces, and then we can add up those approximations to get an approximation for the total area, okay? And so the idea of this is we're going to take each piece and we can approximate it as a trapezoid. So what you can see that I've done over here is I just am ignoring the curvy part that's at the very top. I'm just going to pretend that you have like a straight line segment there instead. And that way I'm going to pretend that we had a trapezoid. So by doing that, we can use the formula for the area of a trapezoid. It's is it asking for a left or right hand? I'm not too sure what you mean by that. Could you maybe elaborate? Well, okay, so it's similar to a response. I see what you're asking for now. Got it. I guess I'm doing neither left nor right. So you can see in a Riemann sum, you would use a rectangle for the approximation. I'm doing something a little bit different where I'm using a trapezoid instead. Okay. And I guess there's a reason why I chose to use a trapezoid rather than a rectangle, although both would work. Okay. Yeah. All right. So as I was saying, so I pretend that you have a line segment on the top that gives me a trapezoid, and I can use this formula for the area of the trapezoid. Okay. Now, this idea where I kind of approximate a nonlinear object with a linear object, that's kind of the main idea behind derivatives. So when you learn about derivatives later in your calculus class, the main kind of idea or the main concept that they are embodying is this idea of linear approximation. Okay. So we could do the same for all four of these pieces. So approximate each piece as a trapezoid. And then we can add up the areas of the trapezoids, and that will give us an approximate area of the shaded figure. Now, notice that this is only an approximation though, so it's definitely some error. And this first piece, maybe if I zoom in a bit, I don't know if you guys can see, oh, there it goes, okay. So you can see that in the first piece, there's a little bit of area that we are not covering with the trapezoid. And over here, there's some extra area our trapezoids are counting, okay? Whoa, okay, that's not, okay. All right, so there's definitely some error when we do this process. So to get a better approximation, if you use more pieces, then you're going to get a better approximation. I guess let me zoom in some more again. Okay, yeah, so that's kind of where I'm going to be going with this. In this picture, I'm using 1, 2, 3, 4, 5, 6, 8, 9, 10 pieces. And looking at this now, there's still some error, but it's not that noticeable anymore. If you look at the top, okay. All right. So yeah, this idea of if we were to continue doing this with more and more pieces until like infinity, if you will. In theory, we would get like the actual area of this figure by letting this process go to infinity. And this is kind of what we use limits for in calculus. So limits are used to find like what's at the end of an infinite process, roughly speaking, okay? And then this entire process of taking a complicated problem, in this case, finding the area of our little figure, and we broke it up into like infinitely many tiny, simpler problems to solve. And then we sort of added everything up at the end to get an answer to our original problem. That process is what integrals help us with. And yeah, I think I kind of summarized all of it here. So limits help us in finding what lies at the end of an infinite process. And then derivatives are used to approximate something complicated or nonlinear with something simple, like something that's linear, okay? And then integrals are a tool for adding infinitely many tiny pieces together And these are kind of the three main tools of calculus that we're going to learn about. Okay, and it looks like we might have a question here. So if you want to either type in the chat or speak up.
May I speak up?
And that's fine.
Speaking of what you were saying in the summary, an integral
Yes.
is a tool to help find an area of an irregular object. What it is in the summary is an integral is the opposite of a derivative. Basically, in other words, an integral on
Yeah, I'm not sure if maybe you cut there at the end, but yeah, so the fundamental theorem of calculus relates derivatives to integrals. And the theorem roughly establishes a sort of like inverse relationship between derivatives and integrals, so that in some sense they're sort of like opposites of each other, actually. Okay, and so you guys will learn about that when you learn about the fundamental theorem of calculus. All right, good. And then in this slide here, I just try to summarize what the calculus is altogether. So I said that calculus is the art of taking a complicated problem and solving it with some sort of like infinite approximation procedure using limits, derivatives, and or integrals. Okay. All right, and I'm gonna stop sharing this real quick. And let me go back to my OneNote. I can get rid of that. Okay, so I want to give like another nice illustration of this kind of process. So some of you may have seen this before, but for those of you who haven't, here's kind of a picture of how to calculate the area of a circle. So how many of you remember what the area of a circle was?
pi r squared.
Yeah, that's correct. Try to move this down. Okay. So some of you might wonder, like, where did that formula for the area of a circle come from? And this image tries to give an explanation of why the area of a circle is pi r squared. So let's try to follow what's going on in this image. So we take a circle, and they're doing something similar to what I did in my slides. Here, they took the circle and they divided it into 8 pieces, okay? With those 8 pieces, they've kind of rearranged them into this kind of configuration. Okay. All right, and so when you do this, right now, this object, it kind of looks like a parallelogram. So it's like, again, if you ignore all the curves on the top and the bottom, then you can roughly think of that as a parallelogram, okay? All right, but to get like a better idea of what the area of the circle is, if you continue using more and more pieces, so instead of using 8 pieces like we did here, here's the same idea, but using 1, 2, 3, 4. I'm counting 15 pieces for this one. And I guess what you're supposed to notice is that this kind of parallelogram object that we've got, it's not as slanted as before it. So it's a little bit more upright. And if you use even more and more pieces, and then again, rearrange them like this, yeah, that was interesting when I counted. Maybe I counted wrong, whatever. what was I saying? Yeah. So if you continue this process more and more, what you see is that this becomes more and more like a rectangle. So at this point, it's almost like upright, and the top and the bottom are almost like perfectly straight. So if we think about if we pretend that this was a rectangle, then we could ask what was the area of this rectangle. And so we know for a rectangle, the formula for the area is base times height. So the height of this rectangle is roughly going to be, or it's going to be equal to the radius of the circle. Okay. So if we think of pretending this is like upright and straight, it's going to have a height of r, the radius. And then as for the base or the width of the rectangle would be equal to. So here, notice that the base of the rectangle is formed by all of the blue pieces, which is half of the circle. So if you add up the lengths of these segments from all the blue pieces, that should give you a rough idea of what the length of the bottom is. So if you guys remember, the circumference or the perimeter of the circle was 2 pi r. But this was only 4.5 of the circle, so it's not going to be a whole circumference, but it's only going to be half of a circumference. So that leaves you with a length of pi r at the bottom. So now if you do like base times height, you're going to get a formula pi r squared for the area, okay? So this is, again, similar to what we did in the slides just now. So this is sort of one way of kind of justifying that the area of a circle is pi r squared. It's the same idea of taking a problem, breaking it into a bunch of tiny pieces, and then somehow putting it all together in a way where you can get a solution to the original problem, okay? All right, so maybe I'll stop for a moment and ask if there's any questions of what I've gone over so far. Okay, so then I'm gonna do one more thing. So let me go back to here. Right, so I'm gonna stop sharing for a brief moment. All right, that's great. Okay, so I wanted to return to my slides because I actually have a couple more slides to go over here. So I'm gonna, ignore that. Okay. So I'm gonna look at another similar situation, and some of you guys may have seen as well. If you're like math geeks who like looking at math jokes. Okay, let's see here. Oh, there you go. Okay. So here we're starting with a circle with a diameter of 1. Okay. And next, okay. Here we have a square drawn around the circle. And because the diameter of the circle was 1, that means the perimeter of the square is going to be 4. Okay. Now, if you remove the 4 little corners from that square. Okay. The resulting shape will still have a perimeter of 4 because like the lengths that you subtracted here and here were re-added here and so forth. So you can kind of continue this process, and each time you remove more and more corners, the perimeter is always going to remain equal to 4. But now if you imagine taking this process to infinity, it seems like that shape is going to converge to the circle, okay? Now, let's go back one. Let's go back to this real quick. Okay. So because that process always left us with a perimeter of 4, when we repeat to infinity, that suggests that the figure at the end should have a perimeter of 4 as well, okay? But thinking back to what the formula was for the circumference of a circle, circumference was 2 pi r, which is the same as pi times the diameter. So on the one hand, the circumference of the circle should be equal to pi. But on the other hand, when we use our little infinite process with the squares and removing the corners, we get something that has a perimeter of 4 at the end of that process. So therefore, it looks like you have some sort of a contradiction saying that the circumference of was actually equal to 4, but also equal to pi. And so therefore, it looks like pi should be equal to 4. Okay. So I guess I just maybe like caution that this procedure, though it's really cool, can be used to solve a lot of problems. The details of it do matter. So you need to like actually be sure that at each step of the process, when you're doing your like approximations, that the errors are not going to like blow up, if you will, when you try to add everything back together. So the details matter. And we're not really gonna get that deep into the weeds, so don't worry about that for today and tomorrow. And in your calculus courses, I don't think you'll be doing too much in terms of getting into the nitty-gritty of the details either. But I just want to give that little cautionary note. So this trick doesn't always work necessarily if you just apply it without considering the details. All right. So I'm going to go back to OneNote. Okay, then. So let's like actually get started now. So as I mentioned, for today and tomorrow, we are primarily going to be talking about limits. Okay. We might get to derivatives maybe at the end of tomorrow, but we're also going to be focusing on limits. And here I've got a nice little picture of the graph of some function. And you can see this function is kind of has a weird looking graph to it. There's some holes in it and some jumps in the graph as well. And I want to use this just to give us introduce the idea of limits of functions. Okay, whatever. And also to introduce you guys to like the notation that we use when we're talking about limits. Okay. So let's say this is a graph of some function f of x, and I'm gonna just look at a couple of aspects within this graph. Let's start over here. I don't know if you guys can see that. No, okay. So I'm gonna be looking at this little jump in the graph first. Okay, so if we kind of like read this graph from left to right, then as we approach from the left, we see that the graph is approaching a y value of 2, okay? And here I can represent that using a limit statement. So what we can say is as x approaches -3 from the left side, okay? This function is approaching a value of 2, okay? For this graph, maybe not quite. There might be a point that's not in the domain. Yeah, there you go. So we'll look at that in a bit. Okay. All right. So now if we were to approach from the right instead of the left, okay. So as x is closer to -3, but approaching from the right, this function is going to this here, which has a y value of 1 instead of 2. And again, we can write down a limit statement to represent this observation. So we can say as x is approaching -3, but this time from the right side, this function is approaching a value of 1, okay? All right. Now, because this function is approaching 2 different values, as you approach from the left and then from the right, altogether, we're going to say that the limit as x approaches -3 of this function f of x, we're going to say that this limit does not exist because the function is not approaching a single value. It's trying to approach multiple values at once. And so you can't really assign one of those values over the other as what the function is approaching. So we would say it does not exist, okay? Now, when we look at what's happening over here, when x is -1, we see that there is a hole there as well. But this time, if we imagine approaching -1 from the left, and also if we approach, or as x approaches -1 from the right, in both cases, the function is approaching this value of -2. Okay? So we could say the limit as x approaches -1 from the left, as well as from the right. Both of these happen to be equal to -2. Okay. And then, yeah, to answer that question, yeah, so again, why was it that this limit does not exist? So I guess the idea is function is not approaching a single value as x is approaching -3. Instead, what we're seeing is the function is approaching 2 different values. It's approaching 2 from the left and 1 from the right. Yeah, so because it's not approaching a single value, we're just going to say this limit does not exist. Okay. But in contrast, at x equals -1, we do see that the limit from the left and from the right, both of them exist and they give the same value of -2. So in this case, we will say that the limit as x is approaching -1 of this function altogether would be equal to -2, okay? All right. So one thing to notice is that it doesn't really matter that there is a hole in the graph, okay, at x equals -1. So when we're talking about the limit as x approaches -1 of this function, we're just looking at value is the function approaching. And so we're not concerned with what value the function is equal to, but only what value it's actually approaching. Okay. So f at -1 is actually undefined because we have a hole in the graph at that point. Okay. But the limit as x approaches -1 is going to be -2 because that's the value that the function is approaching. And then just lastly, let's take a look at what's going on at this point. So that's all that's happening at x equals 2. So if we look at the limit as x approaches 2, but from the left side, okay. So approaching from the left, this function approaches a y value of 1. So we would say the limit approaching 2 from the left is 1. But as x approaches 2 from the right, this function is approaching a y value of 3 this time. Okay. So again, you could write down this limit statement, the limit as x approaches 2 from the right of f of x is equal to 3. And so again, we have a situation where these two limits are not equal to each other. So altogether, what value is the function approaching as x approaches 2? We would say that this limit does not exist because it's not really approaching any one value as x approaches 2. Okay. Now I did put a little dot in the middle here in the graph though. So what that dot represents, it tells us that the function f evaluated at x equals 2 is going to be equal to 2. Okay. So again, this is just to sort of emphasize that when you're looking at limits, you don't really care about what your function is equal to at that point. So again, with limits, you're more interested in what value is your function approaching. Okay. All right. So here I'm just kind of illustrating graphically the idea of limits of functions. And I'm kind of introducing you guys to the notation that we use for limits as well. All right. Any questions about what I just went over? Yes.
Can you give us example what this limit would be used for in real life?
Yeah. So I guess maybe like if I were to relate it to what I went over at the beginning, here the idea is you're letting x get closer. Like let's look at I guess let's look at this one here again. Okay. So here we're talking about the limit as x approaches -1. So I guess the idea is like we're letting x get closer and closer to the value of -1, but we're never actually looking at what happens when x is equal to -1. And that's why we don't care about what happens when the function, like what the function is doing at x equals -1 exactly. Here, we're just thinking as we let x get closer and closer and closer, letting it get like sort of infinitely close, but not actually arriving at -1. We're asking like what value is our function going to approach? And so here, graphically, we can kind of infer that the function approaches this value of -2. So that's kind of how that relates to what I talked about with limits before, how they're talking about like limits are used to determine what lies at the end of some kind of infinite process. So here it's like you have an infinite process of letting x get closer and closer to -1, and you want to know what's going to happen at the end value does your function end up approaching. Okay.
Got it. Thank you.
All right. Sure. I answered the last question first. So why is f of 2 equals 2? That's just because of this dot that I have here. So that dot is part of the graph of our function. So at x equals 2, the point on the graph is up here that has a y value of 2. So that means that f evaluated at 2 would be equal to 2. Okay. Now, it's the limit that ends up being undefined or does not exist as x is approaching 2. And that's because the limit is different values as you approach from different sides. Okay. And then, yeah, so here I was looking at the points where there were holes or jumps in the graph to talk about limits. But I didn't have to look at just those points. I looked at any other point on the graph. So maybe like as an example, let's look at this point here that I'm just now adding in red. Okay. So that's at x equals 1 and the y coordinate is -1. So that means f evaluated at 1 is -1. Okay. But if we look at the limit as x approaches the value of 1, whether you approach from the left or from the right, both approaches will give you the same answer. The function is going to end up approaching this y value at -1. Okay. So this is a point where the limit actually matches the value of the function. And whenever this happens, when the limit is actually equal to the value of the function at that point, we say that the function f is continuous. And we'll maybe talk a little bit more about continuity, I think tomorrow, perhaps. So I guess intuitively, to be continuous just means that there's no hole or jump in the graph. Okay, and I guess that kind of makes sense because you would maybe think just like from what the word sounds like, right? If there's a break in the graph, it sounds like it's not continuous there. So this function is like not continuous at x equals -3, and like it's not continuous at x equals 2, for instance. But it is continuous at all the other points where there was not like a jump in it. Yes.
I have some target. A hole, if a graph has a hole, that means it's a removable discontinuity.
In this case, well, let's see here. Yeah, this one here in particular is called a removable discontinuity. That's correct.
And if a graph has a jump, like from
this
like
one,
from
yeah.
f of like right there, what you're pointing on the screen, that is a jump
Yes.
discontinuity.
Yes. Yeah, so there's like different types of discontinuities that a function can have. Yeah, so this one's called removable because you can sort of remove this discontinuity if you just sort of like fill in the hole base. But for discontinuities like this one, it's a non-removable discontinuity because there's no way that you can like this hole is already filled in, but that doesn't fix the jump in the graph. And if you try to fill in this hole instead, again, that doesn't fix your issue. So there's nothing you can do to repair this break. But this break here, you can repair it just by like filling in the hole, roughly speaking. So that's why this one is removable. Okay. And so I'm going to look at another picture now. So I'm going to scroll down a bit. Okay, so this picture doesn't have any holes or graphs in it, but it does have some vertical and horizontal asymptotes. I don't think they're showing up too well, so I'm going to try to quickly in red indicate where those asymptotes were. So here you got some vertical asymptotes, and here's another horizontal asymptote. Okay. All right. And we went over horizontal and vertical asymptotes a little bit on Monday. I'm going to go over them a little bit more today, assuming I have the time to get to that part. But we can sort of characterize horizontal and vertical asymptotes using statements. And so I'm going to roughly indicate how that works right now. Okay, so let's look at this horizontal asymptote first. So that's at a y value of -3. Okay. And what's happening is this function, if we just follow it further out and out to the left, this function is approaching this value of -3. Okay. So roughly, we can say something like the limit of this function ends up being -3 as x is approaching. And so if you're going out further and further to the left like this, it's kind of like you're letting x approach -infinity because you're just letting it slide all the way out to the left side of the number line. So we're going to write it as the limit as x is approaching -infinity of this function f of x equals -3. So this limit statement is kind of representing the fact that we have a horizontal asymptote here. Okay. And I guess what I'll do is I'll look at this horizontal asymptote next. Okay. So this one's kind of similar. This time we have the function is approaching a y value of +2. So the limit of f of x, we're going to say, is equal to 2 as we go further and further out to the right, which is like saying we're letting x go further and further out towards infinity. Okay. So therefore, we're going to have the limit as x approaches infinity of this function f of x equals 2. And then if we look at the vertical asymptotes next, let's look at this one here first. Okay. All right, so this vertical asymptote is located at x equals -2. Okay. So let's look at what's happening to the function as x approaches -2. And we'll look at it both from the left and from the right. Okay. So as we approach -2 from the side, okay, this function, because of the vertical asymptote there, you can see that this it just keeps going up and up and up. The closer you get to -2 from the left, the further up it's going. So we would represent that by saying, as this is approaching -2 from the left, this function is approaching positive infinity, because as you go up and up, the y value is just going higher and higher and just going out to infinity. Okay. And it's the same as you let x approach -2, but from the right side. This function, again, it just shoots upwards. So the y value just goes out to infinity. Okay. And in this case, you could say, again, because the limit from the left and the limit from the right are giving us like the same value, if you will, you could say that the limit as x is approaching -2 of this function is equal to infinity. Okay. All right. Now, just looking at the other vertical asymptote that we have over here. Okay. You can make similar statements. That vertical asymptote is at x equals 2. So if you try to examine the limits as x approaches 2, again from the left and then from the right, okay. Now in this case, as x gets closer to 2, but from the left, okay, here the function is not going up, but it's actually just shooting straight down instead. So here the y value is going to be approaching negative infinity if you just keep going downward. So we're going to say that this function approaches the value of negative infinity as x2 from the left. Okay. As x approaches 2 from the right, though, we can see that the function is going to go out to infinity. So the limit as x approaches 2 from the right is going to be positive infinity. And so here, the left and the right side limits give you different answers. So you could say the limit as x approaches 2 altogether will not exist. Yeah. All right. So those are just like different examples of limits. At least when we look at graphs of functions. Okay. And I'm going to be doing like some more like analytic examples where we actually have to like do some work and crunch some numbers. But I wanted to start with this like sort of graphical illustration of the idea of a limit of a function. Okay. Any questions before I move on?
Yes, is limits as infinity is acceptable? Like what type of jump in that graph would be named?
So I guess in order to have an infinite limit like you have here, or like here where you have like infinite limits again, positive and negative, essentially what's happening is you have a vertical asymptote at that location. Okay.
Yeah.
So infinite limits occur wherever you have a vertical asymptote.
Yeah. So the continuity
Yeah.
is in come to is this a continuity in limits or?
In terms of being continuous, so like for example here at x equals -2, where you had that vertical asymptote, we would not say that the function is continuous at -2 because the function didn't break in the graph there, so it's like not going to be continuous. Okay.
Okay. So limits can be a number or a infinity.
Yes, that's right. Yes. And yeah, infinity is technically not like an actual number. So here we can say so here when we're saying the limit is infinity, this is actually maybe still technically considered does not exist as well, because infinity is not like an actual number, but you can be like a little bit more precise in this case. So it does not exist, but here you can be a little bit more precise, and that's because it's giving you an infinite limit. In this case, a limit of positive infinity.
Okay.
Okay. All right. So we looked at how to find limits of functions if you are able to like stare at its graph. So now the question is, like, if I give you a function without its graph, can you still calculate the limit? Okay. So we're going to look at some examples of that now. So let's look at some like really simple examples real quick before I move on to some more interesting cases. So here's the first example. So it's just the limit as x approaches 2 x squared minus 5 plus 3. So the idea of this is as x gets closer and closer to 2, what value is this function here approaching? Okay. And so what you can do here is just kind of plug in 2 for x and see what happens. So if I plug in 2 for x, that's going to be 2 squared minus 5 times 2 plus 3. So it's 4 minus 10 plus 3 is negative 3, right? Okay. So when x is exactly equal to 2, this function will be equal to negative 3. And so then what happens if x is like really close to 2? Well, I guess it's reasonable that, if x is really close to 2, x squared should be really close to 4. 5 times x should be really close to 10 if x is really close to 2. So I guess like intuitively, it seems that this function should be getting closer and closer to the value of negative 3 as x gets closer and closer to 2. So to evaluate a limit this one here, which is a pretty simple limit, all you have to do is plug in the value of x into the function, and that's going to give you your answer. Okay. And we'll see cases where that's not the case real soon. But if you just plug in the value of x into your function, and that gives you an answer, you can generally assume, at least in your calculus class, it's probably going to be the right answer. Okay. Negative 3 just came from plugging in 2 for x. So that's kind of what I did over here. You just plug in 2 for x, and that gets you a number negative 3. And then the idea is as x to 2, for a simple function like this, it should give you something close to the value of the function. Okay. Okay. So let's take a look at another example. It looks a lot more complicated, but it's actually not that much more complicated. Okay. So we have as x approaches -1, and then let me try to blow that up. Okay. And we have a function that looks like extremely messy and ugly. Okay. But when you're evaluating limit functions like this, so again, what I would do is I would just start by plugging in the value that x is approaching into everything. Oh yeah, so maybe if you weren't sure about that, the reason why I was plugging in 2 for x is because we were doing the limit as x approaching 2. Maybe that's the part that you might have missed. Right. And then what I'm going to do here is I'm just going to start plugging in -1 for x this time. Okay. So if we plug in -1 for all the x's, let's see what we get. So in the exponent of the e, we have 3x squared minus 2x. So if you plug in -1 for x, I think you're going to get an exponent of 5. Okay. And then that's multiplying sine of pi x. And again, I'm going to plug in -1 for x. So you're going to get sine of negative pi if you do that. Inside the square root, again, plug in -1 for the x. You're going to get 3 plus 1, so square root of 4. And then in the bottom, you're going to get, replace x with -1. And then we have the natural log. And inside the natural log, if you plug in -1 for x, it's 1 plus 3 plus 1. So that's going to be natural log of 5, it looks like. Okay. All right. Who can tell me what sine of -pi would be equal to? You put a question mark there, so are you not confident in that answer? So does anyone agree, or does anyone disagree maybe? It is correct. So yeah, sine of -pi is 0. So that means this whole part goes to 0. Oh, I meant to switch colors. Okay. Yeah. Okay, very good. So that leaves us with square root of 4, which is 2 over -ln 5. And natural log of 5 is some kind of decimal number. You could use a calculator if you wanted to, but in your calculus courses, you'll be able to leave an answer like this though. So just leave your answer as -2 over natural log of 5. They usually do not like it when you give them a decimal answer. So they will prefer you to leave your answer looking like what we have here instead, okay? If you're doing like online assignments, sometimes the online platform will accept the decimal answers, but for your like paper assignments, the professors will generally be looking for an expression like this as an answer instead of a decimal, okay? Okay, so what we've seen so far is that to evaluate the limit of a function, you just plug in the value that x is approaching to get your answer. At least so far, that's what it looks like from these two examples. So I want to consider situations where that is not the case. And that's going to lead us to this next topic of indeterminate forms. Okay, so let's take a look at this limit up here right now. Where did the 5 come from? Let's go back real quick. Yeah, scroll down, okay. We were plugging in -1 for x. Oh, okay, there you go. Yeah, so when x is -1, plug it into the natural log. So here you get -1 squared is 1 plus, well, I guess I'll write it out real quick because my cursor's not really working. All right, you got it? Okay, good. Okay. So yeah, it's just plugging in the -1 for x. No, that's all right, yeah. And no, we're not going to do L'Hopital's rule because you need to know about derivatives in order to use L'Hopital's rule, and we're probably not going to get that far into derivatives today or tomorrow. So, although you could evaluate this limit using L'Hopital's rule, though, that's correct. All right. But let's look at this limit here. So it was limit as x approaches 0 of sine x over x. So if you try the same technique that we did in the previous two examples, and just try to plug in 0 for x, sine of 0 is 0, and then you plug in 0 for x, so you get 0 both in the numerator and in the denominator. Now remember that division by 0 is not defined. So this expression 0 over 0, it doesn't it's not like an actual ding, if you will. Okay, it's not like a mathematical object that actually exists. Okay, so when you're working with limits and you get a 0 over 0 situation like this, what's happening is we're saying that the numerator is getting really close to 0, and the denominator is also getting really close to 0. Okay, so it's not that you actually have a 0 over another 0. The idea here is that you have something really close to 0 in both the numerator and denominator. And when that happens, we refer to 0 over 0 as an indeterminate form. The reason why we call it that is because we cannot determine the value of the limit just by knowing that the numerator and the denominator are approaching 0. Okay. And I want to kind of illustrate that just with these two really simple examples. So in the first limit statement, we have, limit as x approaches 0, x over x. So if you were to try to plug in 0 into that function, you would technically get 0 over 0 when you do that. Okay. But in this case, if you have x over x, you can just simplify that, right? X over x reduces to just 1. And then in this case, 1 is just a constant. So as x is approaching 0, 1 is going to just remain constant equal to 1. So altogether, this constant function of 1 is going to approach the value of 1 as x approaches 0. Yeah?
May I speak up?
Yes.
Simplifying this to 1, if you did it using L'Hopital's rule, you would get the same answer. Basically,
that's correct.
the
Yeah.
derivative of x is 1.
That's correct. Yes. Yeah. So now, I guess I should also mention this. So yeah. So again, we are not going to be using L'Hopital's rule just because that involves knowing derivatives, and not necessarily everyone has already taken calculus. So we're going to be avoiding L'Hopital's rule the next 2 days, actually. Okay. But that reminds me, because we had a meeting with faculty recently, and they kind of got onto us about this. So make sure that when you guys are doing your homework, that you do not lose L'Hopital's rule to answer your problems, especially, or at least if the class has not gone over L'Hopital's rule yet. Okay. So like your first couple of assignments, you may have some problems that you can evaluate using L'Hopital's rule. In the class, they wouldn't have actually gone over L'Hopital's rule yet. So if you try to use L'Hopital's rule, they may not be accepting your solution. So try to stick to what the class has actually gone over when you're doing your problems, okay? Because we actually kind of got into trouble recently because some of our tutors were teaching students L'Hopital's rule, and they hadn't actually learned it yet in class. So just so you guys know that. X over x just simplifies to be equal to 1, right? Like 2 over 2 would simplify to just be equal to 1. So really, like any non-zero number over itself, that always reduces to 1, okay? I kind of apply it here afterwards. So it's like you try to plug in 0 for x. There's no x that you can plug into, so the answer just will be equal to 1, okay? Yes. Now, if you get something like over 0 instead of 0 over 0, I will talk about that later. So for now, let's focus on 0 over 0, but I will get to that in a bit. Okay. Now, and this second limit here, it's basically the same as the first one, except I put an extra 2 in the numerator. So again, it's actually, if you try to plug in 0 for x, it kind of gives you this 0 over 0 indeterminate form. But if instead of plugging in 0 for x, you first simplify this expression, 2x over x, the x's will cancel out. So really, that expression simplifies to just be equal to 2. So then what's happening as x approaches 0? Well, 2 just remains equal to 2. So the limit here is just going to be equal to 2. Okay. Here we had two limits that gave us a 0 over 0 situation. But when we actually did some math to figure out what the limit is, one of them gave us an answer of 1, the other one gave us an answer of 2. Okay. And of course, you could change the number 2 to any other number to get a different answer for the limit. So I guess what I'm trying to illustrate with these examples is when you get over 0 in a limit, the answer could really be any number. It could be 1, it could be 2, it could be any other number. Okay. So that's why we call it an indeterminate form. You can't determine the answer just by knowing that it was a 0 over 0. Okay. So anytime you get 0 over 0 in a problem, you will need to do something, I guess, like clever, if you will, to figure out what the actual limit is. And 0 over 0 is not the only indeterminate form. So here I've given just a couple other examples of indeterminate forms. Okay. We're not really going to look or study most of these other indeterminate forms, but I just wanted for you guys to be aware that there are other indeterminate forms aside from 0 over 0. So infinity over infinity is an example of an indeterminate form. Basically, what this means is that you have something big in the numerator and something really big in the denominator. So when that happens, it's hard to say what the ratio will be equal to, because it depends on just how big the numerator and denominator are relative to each other. So this is going to be another indeterminate form. Here is an example of a limit that will give you an infinity over infinity indeterminate form. So as x is approaching infinity, then already you can see the numerator, x, will be going to infinity. And the denominator, if you just maybe remember what the graph of e to the x looks like. So you guys might remember that the graph of e to the x looks something like this. So as x goes further and further out to infinity, this function goes further and further up to infinity. So roughly, you can think of e to the infinity as being infinity, if you will. All right. And then 0 times infinity, that is another determinate form. Because what's happening here is you don't have an actual 0 multiplying an actual infinity when you're working with limits. What's going to happen is you're going to have that's like approaching 0 times something that is approaching infinity. So as I take a really small number and multiply it by a really big number, what's going to happen? And so again, it's hard to say. It depends on how big and small these are relative to each other. So that's why we call this an indeterminate. And then here's an example of a limit that will give you a 0 times infinity indeterminate form. Okay. Here, x is approaching infinity, so this first term is already going to give you the infinity part. And then if you look at the e to the minus x, here you can look at the graph of e and see that because of the minus in front, the exponent is really approaching negative infinity. So looking at the graph of e to the x, as x, the exponent, gets closer to negative infinity, you see that the exponential approaches 0. So you can roughly think of it as e to the minus infinity is equal to 0. Okay. So you're going to get sort of like infinity times 0 if you try to plug in infinity for x into here. Okay. And then just one more example of an indeterminate form is when you have 1 to a power of infinity in a limit. And here's an example of a limit that gives you this 1 to the power of infinity indeterminate form. So if you try to plug in infinity for x, well, I guess maybe I should talk about this then, because so just like if I were to just like sort of naively plug in infinity for x right now. Okay. Here, I have just a number p in the numerator. So I just wrote down like a generic variable, but when you have a number divided by infinity in a limit, we do consider this to be equal to 0. And we'll talk more about types of rules of like how infinity works later. But when you have a number divided by infinity, we consider that equal to 0. That's just because when you divide by a really big number, the result is going to be something really close to 0. And that's the idea of this kind of expression. Okay. So that means inside the parentheses, you're getting 1 plus 0. So roughly, you have this 1 to the infinity indeterminate form. Okay. But we won't be able to show this today or tomorrow, but you will learn in your calculus class how to evaluate this type of limit. And if you try to apply the techniques that you will learn to this problem, you'll actually find that this limit evaluates to e to the p. Okay. It's particular when p is equal to 1. You do get this kind of like famous equation that the limit as x approaches infinity of 1 plus 1 over x raised to the power of x will be equal to the number e. Okay. So sometimes you'll see people use this limit as like the definition of the number e. Okay. So that's kind of interesting how the number e is appearing in this formula, perhaps. All right. Now, so someone asked the question, isn't 1 to the infinity equal to 1? Here, the reason why we consider 1 to the infinity indeterminate is, so again, since we're working with limits, we don't have like an actual 1 being raised to an actual infinity. What's really going on is you have something that's getting really close to 1 that's being raised to a really, really big power, like close to infinity, if you will. So when we write that 1 to the infinity, it's not that you have an actual 1 to the infinity. So again, in the context of limits, you have something approaching 1 being raised to the power that's approaching infinity is what's happening. And when that happens, yeah, that could be any value. So here, depending on the number p, that affects the value of the limit here. So this kind of shows you that when you get 1 to the infinity, there's like a whole range of values that it could possibly be equal to. Okay. All right. Now let's do some actual problems now. Okay. And yeah, is there a question? All right. So let's look at this first example here. It looks not that bad.
X
Okay.
bình cộng 5
Okay.
cộng 6 X bình.
So when you have a problem like this, again, I would first just recommend trying to plug -2 in for x. So if you try to plug in -2 for x, in the numerator, you're going to get -2 squared is 4. 5 times -2 is -10 plus 6. And then in the denominator, -2 squared is 4. -3 times -2 is plus 6. And you got the -10. Okay. So in this case, you do get this kind of 0 over 0 situation. So it's giving you this indeterminate form. So in order to evaluate the limit, we have to do something other than just plugging in for x. Okay. So the trick to a problem whenever it's just like a polynomial over a polynomial. So whenever it's a rational function, yeah. The trick is going to be to try to factor your numerator and your denominator first. Okay. Okay, so someone tell me how to factor the numerator. Yep, x plus 3, x plus 2. And then tell me how to factor the denominator. Yeah, x minus 5 and x plus 2, very good. If you factor the numerator and the denominator, notice that you are able to cancel out what they have in common. So then after you make the cancellation, what you can do is try plugging in -2 for x again. So this time, if you plug in -2 for x, in the numerator, you're going to get -2 plus 3. In the denominator, you're going to get -2 minus 5. So it looks like the limit is going to be equal to 1 over -7, so -1/7. Okay. This is kind of like one strategy that you see for how to deal with a 0 over 0 indeterminate form. If it's just working with polynomials like this, just factor them, cancel, and then after you cancel, you can plug in the value for x. And then, yeah, what's happening here in the graph is that, and I guess we kind of talked about it on Monday, right? That what's happening is for the graph of this function, there's going to be a hole at x equals -2. So like roughly, the graph will look something like this. At -2 for x, let's pretend that was -1/7. There's going to be a hole at that point. And, you know, the function might be doing something like this at that point. Okay. Yeah, so the function is not defined at x equals -2, but according to our work up here. As x is approaching -2, the function is approaching this value of -1/7. So that kind of indicates you have this kind of situation going on in its graph. Yes.
I have something to add on regarding this.
Yes.
With the function you just gave,
Yep.
you use by factoring the numerator and the denominator, and by canceling the common terms, you can do it this way or using L'Hopital's rule in this situation.
That's correct, yes.
Whereas in the situation, if you had something like sine of something divided by tangent of something, then in that situation, you have to use L'Hopital's rule.
That's correct, yes. So L'Hopital's rule, I guess people keep mentioning it. So for those who don't know, L'Hopital's rule is a technique to deal with limits whenever you have a 0 over 0 or infinity over infinity indeterminate form. So it's a pretty powerful technique, which is why everyone keeps trying to use it, because it just works a lot of the time. So, but yeah, that's good comment. But again, we will not be using L'Hopital's rule though over the next 2 days. Okay. All right. Okay, so now this function, this limit did give us a 0 over 0 indeterminate form. So the idea is you have to somehow like remove that 0 over 0 situation in order to find the value of the limit. And here we were able to remove that 0 over 0 situation by factoring first and canceling. Okay. Right. And maybe like a quick tip, which is since the numerator and the denominator were equal to 0 at x equals -2, that kind of tells you in advance that x plus 2 is going to be a factor in both the numerator and the denominator. Because remember, for the polynomial to be 0 at x equals -2, that means x plus 2 had to be one of its factors. So you can kind of see what's going on here. Okay. All right. So let's look at some other limits. Okay, so this one involves a square root in it. Let's try, plugging in -1 for x real quick. So if you plug in -1 for x, you're going to get 9 in the square root minus 3 over, and so you plug in -1 for x. So -1 squared is 1. You get minus -1, so plus 1, and then minus 2. And here you can see that, again, this is sort of a 0 over 0 indeterminate form situation. Okay. So because you're getting 0 over 0, that means we have to do more work in order to actually evaluate this limit. Okay. So there's a certain trick that we use whenever you get a 0 over 0 indeterminate form and the problem involves square roots like this one. It sounds like some of you might already know what the trick is, so does anyone maybe want to share in the chat? And don't say L'Hopital's rule. Well, all right, so maybe it's too hard to type out, or maybe you guys are not sure what to do if you can't use L'Hopital's rule. So the trick to a problem like this one is to multiply the numerator and the denominator by the conjugate of the numerator in this case. I guess in general, you want to multiply by the conjugate of whatever has the square root in it. So the conjugate of the numerator is just changing the sign in the middle to be minus instead of plus. So I guess maybe like real quick, these expressions a plus b and a minus b are sometimes called conjugates of each other. And what's useful for us with conjugates is if you multiply the two of them together, some of you might recognize that this is how difference of squares factors. Okay. So the idea here is that if A or B have a square root in them, if you multiply by the conjugate, everything gets squared on this side, and that's going to remove a square root if you had any. Okay. So we'll kind of see how that works in this example problem here. So I'm going to multiply by the conjugate of the numerator. And whatever you do to the numerator, you have to do it to the denominator as well to ensure that you're still working with the same problem. Okay. All right, so let's try to simplify this. So in the numerator, when we multiply these two together, you're going to get that difference of squares. This is similar to rationalizing the denominator, but when you rationalize the denominator, you don't always have this kind of conjugate thing that you're doing. Like I gave an example on Monday, but like as a brief aside. So like something like this would be like rationalizing the denominator. But it's not really making use of conjugates the way that I am here in this example. Okay, so not quite, but it's kind of similar. And then also just as a reminder, in your calculus courses, you do not need to do this. So your calculus professors don't actually care if you have a square root in the denominator. So you don't need to worry about rationalizing it in that case. There you go. Okay. I was waiting for the e-learning to update what I had written down. Okay. All right. So here, so we're going to multiply the two fractions together. So to do that, we just multiply the numerators and the denominators. So in the numerator, when you multiply by conjugates, we know that it's going to result in a difference of squares. Okay. So we're going to end up getting the square root of 5x squared plus 4 squared minus 3x squared. Okay. So it's just using this idea here. So you should get a squared minus b squared, if you will, when you multiply by the conjugates. Here, the a was the square root, and b was the 3x. Okay. All right, in the denominator, what I'm going to do is I'm just going to leave it as x squared minus x minus 2, and then times this whole thing with the square root in it. Okay. Oops, minus. Okay. All right. So let's keep trying to simplify what we have. I guess I'll continue over here. Now in the numerator, you have square root getting squared. So those are going to cancel each other out. So you're just going to get 5x squared plus 4, and then 3x all squared is going to be 9x squared altogether, okay? And then I guess I'll kind of jump ahead a little bit here to try and save a little bit of time. Okay, but I want to factor the polynomial that was in the denominator. So x squared minus x minus 2, who can tell me how that factors? Yep, good. So x minus 2x plus 1. All right, good. And then let's see here. In the numerator, you can combine the 5x squared minus 9x squared. So that's going to give us, oh, I meant to change color. Oh, it says, oh, that's weird. Okay. Yeah, so that reduces to minus 4x squared plus 4, okay? Okay, so I factored the denominator earlier. I'm going to do the same and factor the numerator as well, because again, I want to try to cancel something out in order to try and remove that 0 over 0 situation that we had, okay? So to factor this, I would probably factor out a negative 4 from both terms first. That will leave me x squared minus 1 after I factor minus 4 from those two terms. And then x squared minus 1, how would that factor?
X plus 1 and x minus 1?
Yeah, okay. So I'm going to write down the results that we have here. Okay. And so once you factor the numerator and the denominator, again, you can kind of see what's happening is we have the x plus 1 appearing in the numerator and the denominator, so you can actually cancel those out. Yeah, okay. Now, as for where that came from, okay. So that was just over here. I took 5x squared minus 9x squared and just combined them to get minus 4x squared, okay? And then you still had the plus 4, so I just carry that over. And then what I did is I factored the minus 4x squared plus 4 that we had, okay? All right. Now, these factors of x plus 1s that we had, these were what were like giving us the 0 in both the numerator and the denominator when we plugged in -1 for x. So now that we've canceled them out, we should no longer have a 0 over 0 situation. Oh, whoops. So at this point, we should be able to try plugging in -1 for x again. So I guess I'm just going to do that at this point, plug in -1 for x. Okay. And let's just see what that gives us real quick. You get 8 altogether in the numerator. here, that's -3 times 6 altogether. So I think you get 8 over -18, which you could simplify, but I'll see my answer like that, okay? All right, so any questions about this example here?
So how would the graph will be? There will be a hole when x is equal -1.
That's so the graph of this original function. What would happen is at x equals -1, there would be a hole here with a y value of -8 over 18. And then again, I don't quite know what the function looks like, so I'm just going to draw something kind of generic. But the graph would be doing something like that. So as x is approaching -1, the function is approaching this value of -8 over 18. Okay. But the function itself is not defined at -1, because if you try to plug -1 directly into the function, you get a 0 in the denominator. So it's not actually defined there. That's why it's going to be a hole instead.
Got it. Thank you.
All right. Let's see here. I think let's move on. So I have kind of 2 more topics I was going to discuss, but I maybe only have time for one of them. So that just means that last one we have to cover the one that I don't cover tomorrow. All right. So this last topic that I have is limits at infinity and horizontal asymptotes is what's being covered by the menu of pens that I have at the top. Okay. So here we can actually give like an actual definition of a horizontal asymptote using limits. So we can say that the line y equals L is a horizontal asymptote for this function f of x if either the limit as x approaches infinity of this function is equal to L, or the limit as x approaches negative infinity of this function is equal to L. So this is just kind of an idea of like going back to the graphs that I kind of drew earlier. If say this is at y equals L here, if you have a horizontal asymptote at this line, then one possibility is that maybe your function is like approaching it like this. And so what would be happening is as x goes further and further out to infinity, this function is getting closer and closer to the y value up here of L. That's what this limit is kind of indicating. Or it could have been a situation where the function was approaching this line that as x goes further and further out to the left. And so that would be as x is approaching negative infinity in this case, all right? But to have a horizontal asymptote, that means that the limit as x is approaching either infinity or minus infinity is equal to that y value, okay? So I'll try to do just a couple of examples to end the day regarding these horizontal asymptotes. I guess maybe real quick, I should say, I kind of wrote it at the top in the title, but these types of limits where x is approaching either infinity or minus infinity, these are sometimes called limits at infinity. So it's kind of thinking like what's happening at infinity or as x goes to infinity or minus infinity, okay? All right, so that's just like a little bit of terminology. So I wanted to try to apply what we learned to some problems. Let's look at this first problem. Now, we're going to find the horizontal asymptotes using calculus, so using limits, okay? But who can tell me, without doing any calculus, just by looking at this function, who can tell me what the horizontal asymptote should be? Yeah. So we went over this on Monday. But for a rational function like this one here, if the degree of the numerator matches the degree of the denominator, which in this case it does, you can get a horizontal asymptote by taking the ratio of the leading coefficients. 3/7 gives you that horizontal asymptote. But now let's see if we can actually get the same result using limits and calculus, okay? So let's look at the limit as x approaches infinity of this function. Okay. Okay, so here, if you try to plug in infinity for x, it kind of doesn't work really well, if you will. You can say that if you plug in infinity for x, that you would get an infinity over infinity indeterminate form, okay? So what's happening is the x squared term kind of dominates everything else in both the numerator and the denominator. So as x goes to infinity, you square it and it just gets even bigger. So it's just going to remain infinite in both the numerator and the denominator. But as for how to rigorously make that argument, there's kind of a trick to these problems, which is, and there's actually slightly different ways of doing this. I've heard people like give slightly different techniques, if you will. The one that I like the most in dealing with these types of problems is to find the highest power of x in the denominator. So I'll focus on the denominator for this. In this case, the highest power in the denominator was x squared. So what we're going to do then is we're going to multiply both the numerator and the denominator by 1/x squared, okay? So since I'm multiplying both numerator and denominator by the same thing, I'm not changing the actual problem by doing this. Now, if I distribute the 1/x squared into the numerator and then into the denominator, I'm just going to write out what I have. Yeah, so 1/x squared. So the x squared comes from looking at the highest power in the denominator. And then whatever the highest power is multiplied by 1 over that for both the numerator and the denominator. Okay. All right. So if we distribute the 1/x squared to every term in both numerator and denominator, we're going to end up with something like this, which looks pretty messy, but it is going to simplify really nicely. So I'm going to simplify this by canceling out some of the x's. This rule, I guess the main rule that I'm going to be using, I guess I should mention it. I mentioned it earlier, but I suppose I need to mention it again over here. But when you're working with limits, whenever you end up with a number being divided by infinity, we can consider that to be equal to 0 in the context of limits. The reason for this is if you divide by a really, really big number, you're going to get something that's close to 0. So like, if that's not too clear, like imagine taking like a pizza, right? And I tell you I'm going to give 1 billionth of that pizza. How much of that pizza are you getting? You're getting almost nothing. So if you divide by a really big number, it's going to practically 0. Okay. All right. And so when we divide everything by that highest power in the denominator, we're going to get a bunch of these situations coming up where you have a number divided by infinity. Okay. So let's just finish working this out and we'll kind of see how that works. The 3x squared over x squared, that just simplifies to be 3. 2x over x squared, you can cancel out one of the x's. But it leaves us with 1x in the denominator when we do that. For 1 over x squared, you can't really do anything, so I'm just going to copy that as it is. For this term here, the x squared, they're going to cancel. So you just got 7. And then I'm going to copy the last term because, again, there's nothing to really do with that one. Okay. Okay. All right, but now if we try to plug in infinity for x, infinity squared is still going to be considered infinity. So the idea of that is just if you have something really big and you square it, you're still going to get something that's really big, so it's still going to be basically infinite. And the denominator is kind of similar, so you get 7 minus 5 over x squared, and when you plug in infinity for x, that's basically going to remain infinite in the denominator. So if we apply this rule over here, 2 over infinity becomes 0, 1 over infinity becomes 0, and 5 over infinity becomes 0. So that's how we get like an answer of 3 over 7 from the limit. And that tells us that this is a horizontal asymptote, okay? Which rule? The one where you divide a number by infinity, you mean? I think limits is the only context where you will see this. But in mathematics, outside of the context of limits, people will generally still consider this to be 0. So I would say it does kind of apply outside of limits, if you will. Okay. And gosh, I have so many good problems to talk about. I'm going to skip that one for sure, because I have some better ones. So I can do this one, or this one. Well, they're all pretty good, but I would like to end with this example here, okay? because I think this one has something really subtle going on in it, which I want to highlight. Okay. So to find the horizontal asymptotes, again, what I want to do is I want to just look at the limit as x approaches infinity, as well as the limit as x approaches negative infinity. Okay. I'm going to look at this example in particular for that. I'm going to start with the limit as x approaches positive infinity. Oh, you know what? It might be better if I, okay. Let me change my problem ever so slightly real quick. It's not a big deal, but I get something extra that I can show you guys if I put this root in the denominator actually. So let's do it like that. Okay. So when you have a problem like this, so it's kind of similar to the one we just saw, except you have a root, in this case in the denominator, okay? We can still kind of apply the same technique though to evaluate this limit, where we want to identify the highest power of x in the denominator, and then divide everything by that power, okay? Now here, because of the square root, we handle that a little bit differently. So in the denominator, the highest power of x that we see is that x squared term. But because it's in a square root, we're actually going to think of it as being just x to a power of 1, okay? So although the highest power in the denominator is x squared, because it's being square rooted, we're going to view the highest power as actually being x to a power of 1 instead of x squared, okay? So that means what I would want to do is multiply numerator and denominator by 1 over x right now, okay? Okay. So we can distribute the 1 over x to, every term again. Now in the denominator, we have that square root there. So when I multiply by 1 over x, I can just put an x below that for now. I'm going to want to bring the x under the square root in order to simplify this. So the way that I can do that is, let's see here, we'll system edit, and the numerator 4x over x simplifies to be 4. Okay, so in the denominator, what I'm going to do is I'm going to replace okay, the x with a square root of x squared, okay? So right now, x is equal to square root of x squared. You can just make that substitution. And the reason why this is beneficial is because what I can do in the denominator here is I can combine these into a single square root, just using properties of square root. Okay. And then once I bring the x squared into the square root like that, I can continue simplifying what's inside of the square root. So the way that I would do that is I would separate that fraction into 9x squared over x squared plus 7 over x squared. All right, and then 9x squared over x squared, the x squared cancel, that leaves you with 9. And then we still have the 7 over x squared term. But now as x is approaching infinity, again, we can make use of the rule that a number divided by infinity is considered equal to 0. So altogether, we're going to get an answer of 4 over the square root of 9, or 4 over 3 from this. Okay? So that tells us that y equals 4 over 3 is a horizontal asymptote of our function f of x, okay? All right, and then it's possible for a function to have more than one horizontal asymptote though. So we also want to consider the limit as x approaches negative infinity, because that limit might give us a different answer, in which case it will give us another horizontal asymptote. And this is the thing that I wanted to highlight in this problem. If we try to do the limit as x is approaching negative infinity, and just give me a minute because I think the pad is kind of frozen-ish. Okay. Okay, all right. There's a small difference that happens when you try to do the limit as x approaches negative infinity, and I want to show you guys what that difference is real quick, okay? The difference comes into play, and I'm just going to add what the difference is in red, okay? The difference is going to come in at this step over here, so I'll kind of highlight it for that. And I mentioned on Monday that it is not true that square root of x squared is equal to x, at least not always. And that's actually kind of why I very slyly did not write an equal sign here, because technically that would have been incorrect. I just wrote like a little squiggle because I didn't know what else to write. But remember, I mentioned on Monday that square root of x squared simplifies to be the absolute value of x, okay? And if x is a negative quantity, then absolute value of x is equal to negative x. So if x is negative, you have to put another minus in front of it to make it positive, okay? So if x is approaching negative infinity, that means that x is going to be a negative number. And if x is going to be a negative number, that means we have to use square root of x squared is equal to negative x. Or if you will, I can multiply both sides by -1 and say x is equal to negative square root of x squared. Okay? So in the step where I replaced x with square root of x squared, when x is approaching negative infinity, I would actually need to replace x with a negative square root of x squared there. So that extra negative sign would carry through to the end. So I'm kind of rushing this part, but just want to try to finish it real quick. So what ends up happening is you're going to get -4/3 when you do the limit as x approaches negative infinity. So that means that y equals -4/3 is going to be another horizontal asymptote. The function will have two horizontal asymptotes altogether, okay? And then I know I pushed it up to the very end, so we'll end the workshop today.